what kind of questions do you guys have for A5? Like which questions do you want to do?
For part 3, question 3.
Part 3, question 3. Okay, so each eigenvalue of a real skew symmetric matrix A is either 0 or purely imaginary. Ooh.
Like I kind of got a solution for like n equals 2, so it's basically becomes lambda squared plus a real number is equal to 0. So that implies for in the case of n equals 2, lambda must be an imaginary number. Can I then generalize it that if I have an n that is even, the characteristic polynomial, well, the root of the characteristic polynomial will be in the form of some negative lambda k plus c, where c is some positive number and k is some even number that is less or equal to n, which implies that this root must be the root must be imaginary. Am I allowed to generalize it like that?
No, I don't think so. No, because I'm pretty sure not every, like for 2 by 2, of course, you have A minus lambda, and then you have B minus lambda,
Oh,
and then
no,
you
it's
have,
skew symmetric. It's skew symmetric.
Oh.
So diagonal is 0, so
Or
it's
just
just negative lambda.
Right, and then you have some number here.
It should not be like negative a.
Right?
Yeah. In that case, it would be.
So for 2 by 2, it does work. So this would just be lambda square minus, no, not minus, plus a squared, which would imply that it is 0 or purely imaginary. But for a 4 by 4 matrix, I don't think this is true. Is it true for a 4 by 4 matrix as well? One, two, three, four, five, six. Oh my god, there are 6 numbers. A1, A2, A3, A4, A5, A6, and then this is minus A1, minus A2, minus A3, minus A4, minus A5, and minus A6. Like, is this true for a 4 by 4 matrix? Because I am willing to bet it is not true for a 4 by 4 matrix. So what does this become? Oh my god, I hate doing determinism. Yeah, I hate doing determinism. Just gonna use Symbolab. Because I don't think it'll just turn into something like this, which is a simple form, right? But this, yeah, I think this is going to turn into something like, or my guess would be turning something into like lambda to the power of 4 plus something times lambda to the power of 2 plus something, right? And you cannot confirm in that case that lambda is just going to be a pure imaginary number. Because if it does, in fact, turn into lambda to the power of 4 plus a squared, or lambda to the power of 4 plus some constant, positive constant, then yes, you can conclude that it is purely imaginary for the even cases. But I'm willing to bet that is not always the case.
Can you explain just what exactly purely imaginary is?
So purely imaginary is real part equals to 0. So if I have z equals to a plus bi, purely imaginary means a equals to 0.
Thank you.
So it means it doesn't have a real part. Where's determinant? Wait, no. What? Does it not have determinant? What? Yeah, okay, that. Okay. Let's go.
Oh shit, I disconnected. What did I miss?
You didn't miss anything.
Am I right or am I wrong?
I'm trying to find that out because I am willing to bet that this is more likely the case than this being the case. I'm more likely.
Wait, no. Should I just say that, like, the root will always be in the form of sum. The polynomial will always be in the sum from lambda to the n, and then lambda to the n minus 2, and then lambda to the n up until lambda to the n minus 0.
Again, like you're trying to make a claim that requires justification. It is not immediately obvious why this is the case. Like, how do you justify that this is always going to turn into, what, the sum of a whole bunch of even powers of lambda? How do you justify it? Right? It's not immediately obvious.
Would I have to use induction to prove it?
In order to prove something like this, induction is probably the way to go if you want to justify that if you have an even skewed matrix, the characteristic polynomial is only going to have even powers of lambda. Induction will probably work, but that is so much amount of work.
I know, like
So,
you have to like reduce an n times 2 to like n's,
Yes. So you have to
and then
basically
it have to be skew symmetric.
It's just it's not worth it to do something like this. So what we can do is we know that A is a skew symmetric, so A transpose equals to minus A. This is something that we do know, right? A is an n by n matrix. A is an n by n matrix. Now, because we know that we're working towards trying to prove that lambda is a complex number, right? So it actually makes more sense when we're considering A times a vector x, instead of just a real number x, it makes more sense to consider for some x in the complex plane. Okay? Because we know that this is going to be complex. So let's just make sure that our vectors are complex to begin with. So we know that this is true for some eigenvalue lambda. This is true, right? Okay. So.
But A is real.
Yeah, and also there's another definition, which is if you recall the definition of norm, which I don't know whether or not if you recall the definition of norm, the definition of norm for vectors, for real vectors, so norm for real vectors, which is for x in Rn, equals to what? Equals to x transpose x, right? Well, square root, but that doesn't matter, right? And we also know that the norm for a complex number equals to z times z bar, where z bar is conjugate. Right? We know that these two are true. So from this, we can basically infer that the norm for a complex vector
Is that c to the n or just c?
Just c. So we are looking at a single complex number.
Question: do these norm definitions depend on the fact we're using like a squared plus b squared square rooted? Is it A22's definition of norm or any norm?
Yeah,
any definition of norm?
This is A22's definition of norm, right? And this is A22's definition of norm for a complex number. So these two are both A22 definitions that we have talked about before, right? So now it actually makes more sense to define the norm of a complex vector as what? As x bar transpose times x, or equals to x transpose x bar. Doesn't really matter. The problem is whenever we're multiplying term by term, remember we're multiplying complex numbers. We're multiplying complex numbers, but the norm.
Don't you need a square root somewhere?
Happy? I just squared this thing, right?
I mean,
because
square
the
root.
problem.
What?
No, I squared this. I squared the norm.
Oh, fine.
Yes. Don't fight me with it. I don't like square roots. Yeah, they're supposed to be a square root too. Norm squared there. instead of this square root. I hate square root. Norm squared. Just to make everybody happy. So because in the end we want a real number, but if we're just multiplying it term by term, if we just do x transpose times x, we have a complex number multiply itself. So a complex number squared. But we know that a complex number squared is not necessarily a real number, right? So it actually makes more sense to just talk about the norm of a complex number instead. So at every single step, we're actually multiplying every single number with the norm of itself, and then add them all together. Right? So this equals to the summation going from 1 to n of xi times xi bar, which we know will definitely give us a positive real value. So we know that the norm square of this complex vector is going to give us a positive real value. Or actually just non-negative. Right? So we need to use this definition. This is important. This is the square for the norm of a complex vector. I'm not sure if Kari ever talked about this. I want to say no, he did not talk about this at all. But it is a direct consequence from our both definition of the norm of a regular real number vector and also the norm of a complex number. Comes straight as a conclusion of those two definitions. Now, what we need in this case, x is a n by 1 vector, right? Lambda x is also n by 1 vector, a times x n by 1, lambda times x n by 1. So what I'm going to do is I'm going to multiply both sides by the conjugate transpose of x, which we know and makes perfect sense because this is an n by 1 vector, and this is a 1 by n vector because we did transpose it, right? So we can do this multiplication and it will make perfect amount of sense. Okay? So this is what we're going to do. Now, of course, lambda is just a number. This is just a single number, right? So on the right-hand side, what we have is just lambda times x transpose x, which equals to lambda, the norm of x squared. Right, so this is what we have. And if you're not using our mic, please mute it. Thank you. So this is what we have. Because lambda is just a number, therefore we can just switch the position sort of willy-nilly. Right? Now, notice that now this is just a number. The right-hand side is just a number. Right? And because these two are equal, we know that this side is also just a number, which we can tell. 1 by n times n by 1 equals to 1 by 1, which means it is a number. Right? So I can apply transpose to this side perfectly well, and it will just still equals to itself. The transpose of itself will just be itself because it is a 1 by 1 vector. 1 by 1 matrix. And we know that a 1 by 1 matrix is always going to be symmetric. Right?
May I ask how it became a conjugate on, so it was lambda, or it was x transpose times lambda to x. Oh, okay. Thank you.
Yeah, I forgot this conjugate. Sorry about that. Okay. So what I'm going to do is I am going to apply transpose only to the left-hand side. Because again, it doesn't really matter if I apply only to the left-hand side or apply it to both sides because a number and a number. Right? So if I apply transpose to both sides, what do I get in the end? I get ax transpose, right, times x bar equals to lambda times the norm of x squared. Right?
Do I need a transpose as well? Oh no, wait, never mind. I'm done.
Yeah, transpose and transpose cancel out. Right? And because we know for a fact for transpose, we have a B transpose equals to B transpose A transpose. Right? It works for vectors too. So we have that. Okay. What is this transpose? Well, this equals to X transpose A transpose. Right? Times X transpose, which equals to lambda squared times norm of X squared. Which also equals to minus X transpose A times X transpose.
We can't really see the left side.
You cannot see this? Okay.
I think it's just an equal sign, isn't it?
Why can you add a negative all of a sudden?
Mm-hmm.
Let's just move it here.
A is skew-symmetric.
Right? Because A is a skew symmetric matrix, therefore A transpose is just minus A, so we have a
right.
minus in the front. Right? A is skew symmetric. Oh, now we have something that is a little bit interesting. Well, what I'm going to do now is, remember, this is a complex number. This is a complex number, right? And they're equal. So what I can do is I can apply conjugate to both sides. So what I'm going to do is I'm going to apply conjugates to both sides. Wait, this equals to okay. Let me check whether or not if I apply conjugate to both sides is necessary. Actually, no, we don't have to take conjugate to both sides. We only have to take conjugate to this. We just take conjugate this. We just take conjugate of AX to lambda x. We can just take conjugate of this. And also remember for Z, for A, B in the complex number, right? A B conjugate equals to A conjugate B conjugate. So conjugate is commutative with multiplication. Right, so what we're going to do is we look at, so there's no implication here. So this is what we end up with, okay? Now what we're going to do is we're going to apply conjugate to both sides. Realize this, A is a real valued matrix. This is from the question. A is a real value matrix. It did say in the question, didn't it? Yes, a real skew symmetric matrix. So A is a real valued matrix. Therefore, the conjugate does not affect A at all. Correct? So the only thing that affects is X. So the left-hand side becomes A times X conjugate equals to, well, we know that lambda can be complex. But in the end, we want to prove that it is complex. So we know that lambda can be complex. So we have lambda bar on top, and now we have X bar.
How did you remove like one X term?
No, I did not remove it. This is just something completely separate.
Sidestep, okay.
Because we know that AX equals to lambda X, right? So all I do is apply conjugate to both sides. Now, what we're going to do is we're going to put this into this. because we have an A conjugate here and we have an A conjugate here. So we're going to go back to star. Star implies minus X transpose A X transpose, which is just lambda transpose X transpose. Right? Because A times X transpose is just lambda transpose X transpose. This is what we've done. Equals to, well, we don't do anything to the right-hand side. But look at this. Look at this. This lambda transpose is again just a number because lambda itself is just a number, right? So I can move this to the front and just multiply these two vectors together. So in the end, I have minus lambda transpose the norm of X squared equals to lambda X squared. That's norm of X squared. Right? Now realize that the norm of X cannot be 0 because X is an eigenvector. Right here. X is an eigenvector, right? Since X is an eigenvector, then by definition, it is not a 0 vector. If it is not a 0 vector, then its norm cannot be 0. So this does not equal to 0. But these two are equal. That means these two has to be equal. Minus lambda bar equals to lambda, which implies lambda equals to 0 plus bi, which means it is either 0 or it is purely imaginary, as wanted. Right? And the reason for that is because we can just write lambda as a plus bi and see what happens, right? So if lambda equals to a plus bi, right, that we have minus this, so minus a minus bi, so plus bi equals to a plus bi, right? So we have minus a equals to a, which implies a equals to 0, right? Which will prove that it does not have a real part. So it's just going to be bi, right? And the only real value for that would be b equals to 0, so everything equals to 0, which is a real number. Otherwise, if b is not 0, we have a purely imaginary number. So any questions? I mean, imagine trying to do this on our exam. Imagine trying to do this on our exam. Like the first time, this proof did not make sense to me the first time either. So it's just, what the heck? Why? Right. And at the left side, this is just a whole bunch of implied, so a whole bunch of double arrows. Because every single one of these are equations, right? They have an equal sign already, so I cannot just put equal signs there, so I have to make them implies. I have to make them arrows. Generally speaking, you don't have more than 3 equal signs in a single line. What were we proving originally? Good question. I lost.
We're proving that a skew-symmetric matrix only has 0 over imaginary eigenvalues.
In this particular case, even dimensional skew-symmetric matrix.
I'm pretty sure
even?
any dimensional skew-symmetric matrix.
It's any dimensional. It's any dimensional.
I mean, like you can just like take what part 2. Like there's one part where you prove that part 1 question 4 is it prove the determinant of an odd dimensional skew matrix is 0. Like,
well, yeah, that is easy. That is easy.
Yeah, so like just okay. Proof.
Yeah.
By part 1 Q4 QED for odd cases.
Part 1 is really easy. It's just part 3, to be honest. Even part 2 is not at all difficult. Part 3, question 3 and question 4 are just fucking hard.
Really? Question 3 is just a like trick, right? It can simplify very quickly.
The thing with question 3 is Not many people realize that this is the definition of a norm of a complex vector. This is the definition. A lot of people don't recognize that. That's for one. And second, this first step does not make any sense. Why on earth? How would you think of, oh, I'm just going to multiply x conjugate transpose to both sides? Huh? Why? Why would you do that? Why? What kind of drug are you using in order to think of, oh, the first step, the only logical step would to be multiply x bar transpose on both sides?
We're on
Nobody's wrong with
tidy.
that. Right? It's like similar to Kaidi's proof of question 4. You know, we're just going to separate it into null space and the range of a, if we regard A as a linear transformation. Again, who would have thought about that? It's just, oh, and we're going to argue using a rank equation, blah, blah, blah. No, nobody's going to think of that. But that's just the way that the proof works. Once you see the proof, every single one of the steps makes sense. Every single one of the steps makes sense, right? The difference, so one of my my abstract algebra professor told me, is that the proof for algebra is usually very simple, which it is. Going from step to step, you're just using the most basic form of operations, like just multiplication, using a little property of a conjugate and stuff like that. So the proof is very simple, but what is difficult is to think of what to do next. That's the problem. That is the difficult part. Whereas what is different is that calculus, it is very straightforward in what you need to prove. It's just that every single step is very difficult. You argue from one step to another step, that is difficult, right? Compared to algebra, which every single step is easy. You just don't know what to do to begin. Once you know what to do, arguments are always pretty easy. So that's question 3. Part 1, question 2. Question 2 is really trivial. It's just you need to think of it a little differently. I can do a very quick proof by contradiction, although I don't like proof by contradiction because we really don't learn much from proof by contradiction. But what we can do is we can assume, so this is part 1, question 2. You want to prove that, you know, ax equals to something, ay equals to something, az equals to something, given that x, y, z are not linearly dependent. And you want to find the determinant. So assume the determinant of A does not equals to 0. What does that mean? That means A is an isomorphism. Right? That implies AX plus AY equals to AZ is equivalent to X plus Y equals to Z, which means X, Y, Z are linearly dependent, which is a contradiction. Done. That's all I really need you to try. Right, because determinant of A is non-zero, it is an invertible matrix, therefore it represents an isomorphism. Right, and if it represents an isomorphism, then this line has to be true. AX plus AY equals to AZ. Well, isomorphism is injective, so that means X plus Y must equals to Z, right? Because it's injective. But they cannot equal to each other because that would mean that they're linearly dependent. But in the question, it is given they are linearly independent, which will arrive at a contradiction. So this cannot be true, therefore must equals to 0. Right? So that's it. All you need to write.
Define the determinant of the matrix, eh?
Yeah, I just proved that determinant has to be 0.
Okay.
Yeah. I assume that determinant is non-zero. I arrive at a contradiction, so that means determinant has to be 0. Which means I found a determinant is 0. Right? It is a linear transformation. Any matrix is a linear transformation. Any yeah. Okay, so that's part one, number two. What other thing do you want me to do?
The Markov chain one, the probability one.
The stochastics one. So let's say, yeah, the following property, Aij is greater than or equals to 0. Yes. Yes, that is a stochastic process. So that A has an eigenvalue of 1, that the absolute value of any eigenvalue of A is less than or equals to 1. Didn't Kaidi do this already? If Kaidi did it, I'm not really inclined to do it again.
But Kaidi's confusing.
Well, I don't suppose I can do any better, to be honest. So stochastic. Well, because every single value is less than or equals to 1, right? What does that mean? That means they're all positive. So that means whatever vector that you use to multiply by the matrix with, the values, the absolute values of every single one of those vectors will get smaller. They will have to be smaller or equals to, right? Because what we do know is that if A is between 0 and 1, right? That means for all real numbers, right? The absolute value of the number itself is going to be greater than or equals to A times R. That's just how that works, right? So you will have a vector, and when you multiply the vector by this matrix, what you will get is that the result of this resultant vector needs to be less than or equals to the vector that you begin with in terms of absolute value wise. It needs to be smaller, right? So that means this value will have to be less than or equals to 1. That's it. Now, the fact that there exists a eigenvalue that equals to exactly 1, I only know the statistics proof of it. I'm not sure if I know the linear algebra version of it. So there is, because for every single stochastic, for every single one of these, this is what we call probability transition matrix. For every single one of these probability transition matrix, well, not for every single one of them, but there exists this thing called limiting probability. So there is a equilibrium that is sort of reaching. Equilibrium would mean that if I have a vector and I multiply by this probability transition matrix, which is a step in a stochastic process, it would just be itself, which means the eigenvalue will be 1. How do you prove that linear algebra in terms of linear algebra? I actually don't know how to prove that in terms of linear algebra.
Actually, question, why is Kaidi asking us to prove these things in the first place? Like, if even you have trouble doing it. Why does Kaidi
regards highly of you guys, okay? He thinks that you guys are very smart, which I sort of agrees, right? And you can achieve things that are a lot better in some way. How do you know that it has an eigenvector? Has an eigenvalue of 1? Oh, well, if we take this matrix, I will multiply by the 1 vector. Row multiplied by column, right? But because every single row So AI1 plus AI2 plus AI3 plus all the way to AIN equals to 1, because every single row sum up to 1. And when you're multiplying by the 1 vector, what you're doing is you're just summing this entire row, right? Because it is the first element multiplied by 1 plus the second element multiplied by 1 plus the third element multiplied by 1 and so on. Well, this is just going to be the 1 vector. Well, guess what? This is an eigenvector, right? Because they're parallel. And what is the eigenvalue? 1. There, proven. Easy. And nothing wrong with that.
Can you repeat the part where you declare A times like 1, the one vector?
So do you want me to repeat this? So this is an n by n matrix. What I'm going to do is I'm going to multiply a n by 1 vector. So every single one of the value inside this vector is going to be 1.
Mm-hmm.
Right? So what am I doing? When I'm doing matrix multiplication, I'm multiplying every single row. I'm dot producting the row and this column here. Right? I'm taking the first row multiplied by this column, second row multiplied by this column, third row multiplied by this column, and so on. Correct?
Mm-hmm.
So let's think of an arbitrary row. If I have a single row from A and I'm multiplying by this vector, what do I get? Well, the dot product of it will be the first element of the row multiplied by 1, plus the second element of the row multiplied by 1, plus the third element of the row multiplied by 1, and so on. Right? That's dot product. So basically, I'm just summing over the entire row. Right? I'm just taking every single element of the row multiplied by 1 and add them together. So I'm just adding the row together. But then every single row add up to 1. This is a given in the question.
Okay.
So all of the entries in here will be 1. So you know that the 1 vector is going to be an eigenvector. And what is the eigenvalue associated with the eigenvector? 1. Right? This is just 1 times this.
The second part?
What do you mean the second part?
Prove that the absolute value of any eigenvalue of A is less than or equal to 1.
Yes, because what we've discussed previously was if I have a whole bunch of numbers that are between 0 and 1, like if I have A that is between 0 and 1, right? Then for every R in the real numbers, the absolute value of AR is definitely less than or equals to the absolute value of R. This is something that we know, right? So when I'm multiplying a random vector, A times V, then the magnitude of this vector is definitely going to be what? Less than or equals to V itself. So if there is a eigenvalue in front of it, then the Then the magnitude of this eigenvector has to be smaller than 1. What you can do is you can just do this, but you have to kind of define what this is. So you can just do that.
Okay.
Right.
And for part 2, question 4, I kind of don't get why delta needs to be sufficiently small.
Oh, that is not what the question is asking. It is asking for a sufficiently small delta, not at why delta has to be sufficiently small. So again, this is another question that Kaidi explained, but even I didn't understand what he was trying to do with continuity. So basically, it is saying you have a characteristic polynomial, yeah? You have a characteristic polynomial. So you have a polynomial, some kind of polynomial. That means for a value right here, let's call this delta, there has to exist such a delta. There has to exist such a delta, right? Such that every value between 0 and delta is not an eigenvalue. So per 2, question 4. Yes. Okay, so let's start with the beginning of this question. The way that I prove it will be very differently from will be similar in concept, but in execution will be very different from what Kaidi does. So I have what I wanted to prove is that suppose that I have a vector, a matrix, an n by n real matrix in this case, right? And A is singular. A is singular. Prove that for sufficiently small delta greater than 0, so there exists, so this is what you want to prove. Can you guys even see that W? I don't think so. Want to prove there exists such a delta greater than 0. So for sufficiently small values of delta, the matrix A minus delta is not singular. So there exists a delta greater than 0 such that the determinant such that for all, I need another letter. For all n for all n for all n between 0 and lambda, A minus lambda is not singular. And n minus, what am I saying? Sorry. For all delta greater than 0, there exists a delta greater than 0 such that for all n between 0 and delta, A minus ni is not singular. So that's what the question is technically asking. That is what you needed to prove, right? So you know that the determinant of A has to be 0, right? So basically, you want to say that there exists such a small neighborhood, right? So if I say there exists a very small neighborhood around 0, right? A small neighborhood, maybe going from 0 all the way to something, delta here, right? Such that every single one of the matrix created by a number here is not singular. That's what the question is technically asking. Not incredibly intuitive. Not incredibly intuitive.
So is it saying that there are more eigenvalues or vectors in there?
There are more eigenvalues, yes. So let's translate what this question is trying to prove. Already, technically, this is already the translated version. And of course, determinant of A equals to 0 is the same thing as saying determinant of A minus 0i equals to 0, which means 0 is an eigenvalue, right? Which is, again, equivalent to P of 0 equals to 0. So if I have a characteristic polynomial, and we know for a fact that 0 is an eigenvalue because determinant of A minus 0i equals to 0, right? Then the characteristic polynomial is going to have a root as 0. Now, determinant of A minus ni is not singular, does not equals to 0. What does that mean? That means n is not an eigenvalue. Right? Which is the same thing as saying P of n does not equals to 0. Okay? Do we agree on these two statements?
Alex,
agreement
does
that-
this mean that any uninvertible matrix will have all determinants equal to all eigenvalues equal to 0?
An invertible matrix will
No,
have the
a
eigenvalue.
singular matrix,
A singular matrix will have an eigenvalue of 0. Yes.
and
So
only
0 is
0,
one
right?
of the eigenvalues.
That's the
No,
only
not
distinction.
only 0. No, not only 0, but 0 is one of the eigenvalues.
So how can I be certain that n isn't one of those other eigenvalues?
Because you wanted to prove that this is not singular, right? So you want the determinant of this to not be 0. You want the determinant of this to not be 0. If the determinant of this is not 0, that means n is not an eigenvalue. Right? Because the definition of the eigenvalue is a minus lambda I equals to 0, but it's not 0, so that means this is not an eigenvalue. Right? And then, which is the same as saying the characteristic polynomial does not have n as a root.
But then, like, can't you just say, like, given that the matrix has to be finite, but there are infinitely many reals between, like, say, any delta and 0, so there is trivially an n such that a minus ni does not equal 0.
You are touching on the field of topology. You're touching on the field of topology. It is actually not trivial at all. How can you state that?
Because,
How
like,
can you
there's
state
only
that?
each matrix has only n eigenvalues, but like, say,
At most
any
n
interval
eigenvalues.
between any like interval between any real numbers is infinitely many real numbers, so, like, which is obviously
Okay.
bigger than n. So that means
How
there's
ma-
always going to be some real number that is not going to be an eigenvalue.
Sure, you can do that, but you have to prove it. You have to prove the statement that you just made. Well,
Which
yeah,
part?
because it has a infinite number of real numbers between any two real numbers, any two non-equal real numbers. I agree, there exists an infinite number of real numbers between them. All right, and you have a finite number of eigenvalues, so of course there has to be a stretch between wanted value and 0 such that there's nothing between. I agree, but you have to prove it. And in this case, you have to prove it topologically, what you've said.
Oh,
And also, how do you know that it has exactly n differences?
because proof by previous lectures. That's what Kaidi does.
You
Proof
prove it?
by assignment. So I'm just like, proof by Kaidi, QED.
Proof by Kaidi, QED. Sure, you can try to write that. I'm not sure how much mark are gonna give for that one. So the problem with this is, yeah. So we want to prove that. So wait, this is what we know. P of 0 equals to 0, and this is what to prove. P of n does not equals to 0. So let's draw a picture. Let's draw a picture of P. Right, this is P of lambda. This is lambda. We know that P of 0 has to be 0, so that means the polynomial has to cross the origin. Okay? So let's just draw some random polynomial that cross the origin. This is an ugly looking polynomial. I don't care, to be honest. Whatever polynomial works. Why is this vertical? It should not be vertical. Okay, so I have some kind of polynomial that looks maybe something like this. I don't know. Okay, so we have this 0. We have this origin here. We want to prove that there exists such a delta. So there exists such a delta, right? Such that between 0 and delta, there's no roots. Well, it is really obvious on saying, well, intuitively, of course, there has to be a delta such that this is the case. But how do you rigorize it? So basically what you said is correct, but how do you rigorize it? Well, you again hinges on the fact that P of lambda has at most n roots. Again, why? On Friday lecture, Friday office hour, I was arguing with Kaidi because Kaidi had this idea of using continuity to prove it. We know that polynomial is continuous, which is true, right? Using continuity to argue that there has to exist this value, which I did not really understand the proof. Instead, what I thought was we can use something called the fundamental theorem of algebra. And you know that this is an important theorem because it got the word fundamental inside of it. Fundamental theorem of algebra basically states, right? If I have a polynomial, let f be a polynomial with complex coefficients. Let f be a polynomial with complex coefficients. Can you see the word coefficient there? Yes, you can. Right? Of degree n. Of degree n. Okay. Then f has exactly n complex roots with multiplicity. And the way to prove it would be using, well, you can either use topology to prove it, or if you learned about complex analysis, you can use things called winding number on how if you take it to the extreme, every coefficient just gets closer and closer towards a circle, right? And when you move smaller and smaller, the rate at which the point goes around the origin is actually exactly n times. So that winding number is n, therefore has exactly n complex root. Whatever, it doesn't matter. This is what you just need to technically know. This is how you're going to argue. Well, there are exactly going to be n different roots for this characteristic polynomial, because we know for a fact that the characteristic polynomial has a power of exactly n. Or lower, but usually it's just exactly n. You have lambda, 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 and
Doesn't assume p lambda isn't just a constant function.
Like, right?
What if I said prove
so
to me that p
now
lambda?
This is how you know that it has a finite number of roots. Any polynomial has a finite number of roots. So as a corollary, any polynomial with real coefficients have finite number of roots.
What if all coefficients are just 0?
This is how you know it is true.
Yeah, but what if all the real coefficients are just 0?
So it has a finite number of roots. Now the only thing I have to care about is, well, to be honest, as long as we select the delta in between 0 and the closest positive root, this will definitely be true, right? So now what we do is we use something called an axiom of choice. So let lambda 1, lambda 2, all the way to lambda k be the set of root of the characteristic function. right? So let's let this be the roots. So this is going to be all of the roots for the characteristic function. Now we don't care about any negative roots because we know that lambda has to be positive. Lambda. I keep on saying lambda. This is not lambda. Delta, right? We know for a fact that delta has to be positive, so we don't care about any of the negative roots. So we only care about the positive root. Kind of ran out of space. Right? So the only thing that I care about is the positive root. So let I need a letter. Someone give me a letter. English or Greek, I don't care. Someone give me a letter. I have a letter here.
Sigma.
Q. Okay, sure. Although Q means national or rational numbers. Do I have more rational numbers? Can I have something that is not used? S. Okay, S is fine. So let S be the subset of this, be the subset of the lambdas, right? So lambda I such that lambda I are positive, right? Now, if S is the empty set, then any delta in the positive reals will do. Right? If the characteristic polynomial does not have any root that is positive, so it does not cross this line at all in the positive direction, so it just maybe goes on all the way up and never touches the x-axis again, then I can literally take this delta to be whatever I want. Right? So basically let delta, so basically pick any delta from the positive, sorry, not equals to, just the positive ones, sorry. Delta cannot be 0. So pick any delta that is positive. Then for all n that are smaller than delta, for all n that is smaller than delta, the determinant of a minus ni does not equals to 0. Otherwise, so it does not equals to 0. Because if not, then n is an eigenvalue, which would imply p of n equals to 0, which would imply n is in S, but S is the null set, which would conclude a contradiction. Okay, so if S is the empty set, so again, the characteristic polynomial has no positive root, right? Then I can pick delta to literally be any positive number, right? So if I pick delta to be any positive number, then for all of the values between 0 and delta, the determinant of a minus ni has to be 0. It has to be non-zero. Because if it is not non-zero, what does that mean? That means n is an eigenvalue, right? If it is not 0, sorry, if it is not 0, so which means if it is 0, then n is an eigenvalue, which means that the characteristic function has a solution at n. Remember, n is positive, right? That means n has to be in S because S contains all of the positive roots of P, but S is a null set. So how does that work? Right? So that means that it's contradiction. So there's a contradiction. Okay? So this is one of the case where S is the null set. Of course, there's also the case where S is not the null set. Right? So if S is not the null set, so that means S does contain some roots, right? Then what we're going to use is something that you learned about in A67. Then, by the principle of Weyl ordering, I don't know if you guys still remember this principle, the principle of Weyl ordering. There exists such a lambda, let's call that lambda prime, in S, such that lambda prime is less than all other lambdas. Such that lambda prime is less than lambda I for all lambda I in S. Less than or equals to would work too, doesn't matter. Basically what I'm saying is, if S is non-empty, remember that S is a subset of this. It's a subset of all of the roots. We realize that all of the roots are finite. That means this set has to be finite. That means this set has to be finite. And we have a finite set of real numbers. Then by the principle of Weyl ordering, there exists this smallest value. Right? Any finite real number set, so any finite subset of the real numbers have a smallest value. Right? You can think of any finite set of real numbers, you can always find the smallest value. Right? So there exists this smallest value. So I'm just going to let delta equals to the smallest value. Then for all n between 0 and delta, the determinant of A minus Ni would have to be non-zero. Again, why is that? Because if not, which means if the determinant of A minus Ni equals to 0, right, that means n is an eigenvalue. Right, and what does it mean to be eigenvalue? It means P of n has to be 0, right? So that means n is in S because n is positive right here, which means n is actually less than lambda prime, which is a contradiction because we picked lambda prime to be the smallest value, right? We picked the lambda primes such that it is smaller than every other element, smaller than or equals to than every other element in the set. Now we just popped up a new element that is smaller than the smallest element. Does that make any sense? No, it does not. Right? So this will arrive at a contradiction. We know that this has to be non-zero. There you go. Not the smallest positive eigenvalue. Yeah. Right? Because set S sets the restriction on all of the positive eigenvalues. Whew. Okay. So this is question 4 from part 2. Part 2, question 4. For sufficiently small delta is greater than 0. So basically, you want to prove that for every value that is close enough to 0, a minus delta I has to be non-zero. My wording is a little bit weird, and also my my lettering is a little bit weird because technically the n should be delta and delta should be something else. But I used a different. I hate myself. Why did I use it? Why did I use a different one? I should have named it something else. So I should just name this like epsilon or something. I should have. You see, I should have named this epsilon. Should have named delta epsilon, and then I should have named n delta. Then it would just make sense with the naming in the question. But now it's a little too late. You just have to live with this. So yeah, remember to do that to match up with the question. Set delta as epsilon and then change n as delta. That'll make more sense to the question. So yeah. Okay. Any questions regarding part 2, question 4? Questions, comments, concerns? What's up? Everybody perfectly understood everything? Everybody know a proof of fundamental theorem of algebra?
No.
Probably not. Right? Everybody at least know why the corollary is true. Right? Too confused to know why I'm confused. Why are you confused? Why are you confused? Why is this confusing? Which part of this is confusing? Oh no. Oh no, what have I done? What have I done? I mean, at the very least, right? You now have two separate versions of this exact same question, right? One done by me and the other one done by Kaidi, right? Both focusing on the property of this characteristic function. So our idea is the same. We're all just using the properties of this characteristic function. And I mean, you just choose the one that is less confusing for you and then just rewrite the proof in your own words, I guess.
So just to kind of simplify it, right?
Why are you sleep deprived? Why are you sleep deprived? You have no school to go to, right? You have no.
What do you call this?
I
If there is no school, what is this
because
called?
all of the workplace clothes and stuff like that. Like, why are you still sleep deprived? I don't get it.
Wait.
I don't get it.
What do if there's no school, what do you call this?
Okay, so for the question that you asked before, which is question 3 from part 1. So let A equals to some random matrix, let B equals to some random matrix, then find the value of A squared, find the value of the determinant of A squared times B inverse times A inverse squared times B squared. Oh, well.
Wait, Jerry.
You know that A inverse and B inverse both exist, right? Because the
Jerry?
question asks you, so I cannot hear
No?
you. Why can't I hear you? Pretty sure I can hear you. Can I
Jerry?
hear you? Can I hear you?
Hello?
Oh no, what have I done?
Very dumb.
Weird.
what? The microphone for this is working, right? So like
Hello?
if I walk further away without raising my voice, you can still hear me just fine. But that means the microphone on the headphone
Yeah,
is working.
but I
But
don't think
speaker volume is at max. Okay. Why does this not work?
technology.
Okay, let me open Spotify. Maybe something else is happening. Okay, this is going to look really bad in the video again. It's just going to be people saying something, and I just fail to hear it, and it's going to sound really awkward. I have no idea how to fix this, honestly. What about if I just turn it to speakers? Okay. You might hear yourself again, but I have turned the speakers, so hopefully this will do. Yes? Okay, now I can hear you, yes. You might hear yourself twice. Sorry about that, but that's just how it's
Can you
works.
hear us?
Yes, I can hear you.
Okay, just to simplify, it's saying that for the matrix A, there is a smaller value of delta that is greater than 0, such that the determinants in between, I guess, that and 0 are not 0.
Yes. So basically you want to prove, the question is asking you to prove for values that are very close to 0, right? The determinant of A minus delta I is not 0.
Okay.
So what I did with this entire proof is I used the incorrect letters. I should have thought about that earlier. If you replace n with delta, and I replace delta with some other letter like epsilon, it will be fine. It will make
Why
perfect
did
sense.
you write down the fundamental theorem of algebra?
Why did I use the fundamental theorem of algebra? Well, I didn't use fundamental theorem of algebra per se, but I used this corollary.
Okay. Yeah, I got the bottom part. Okay. Thank you.
Yeah. So the bottom part, the corollary, is a result from the fundamental theorem of algebra, which is why I wrote both of them down.
Thank you.
If I just write a corollary, it does not make any sense. But with the fundamental theorem of algebra, then this corollary is very easy to see why the corollary come from this, right? Because I mean, this has exactly n complex roots, and real roots are just a finite number of real roots. Right, real roots is just a subset of the complex root. So I use that. Okay, tech support rollout. Yeah, why don't you come to campus and help me fix this? I'm in SW309. Be here in 20 minutes. So part 3 Q1 hint for 2 and 3. What? Part 3 Q1. That I diagonalize the matrix this, and this. What? It's okay. I guess. I don't see why it is hard, but which part can I erase? Let's erase this part. It is a computation question, right? Like I really do not want to do computation questions, but for the sake of being a nice person, which I am, I will just do that. So
wait, actually,
there are two
question.
ways to do it.
Question.
Mm-hmm.
Would just like The second part, G, just the diagonal matrix of A, but every diagonal is just sorry, part 3. It's just part 1, but just every diagonal entry is just squared, well, raised to the power 100.
Yeah, exactly.
Okay, great.
Yeah,
And
because
part 2.
so if A equals to Q multiplied by lambda multiplied by Q inverse, then A squared, which is A times A, is just Q times lambda times Q inverse times Q times lambda times Q inverse, which is just, well, this is just I, right? This is just Q lambda squared Q inverse. Well, right? And you can just stack it up. You can just stack it up. So A to the power of n will just simply be Q times lambda to the power of n times Q inverse. Right? And what is lambda to the power of n? Well, lambda is a diagonal matrix, right? Therefore, yeah, it is because it is a diagonal matrix, you just raise every single element to the hundreds when you're just multiplying itself. Now for 2, there are 2 ways to do it. You can either do it a dumb way, which is just find what a to the power of 3 and a to the power of 2 or something like that. You can do it that way, which doable. I do not like that. Or what you can also do is, so in order to do question 2, you have to do question 1 first. So let's do that. So A is 1, 2, 4, 3. If it is 3, 4, it is actually linearly, not linearly independent, whatever. 1, 2, 4, 3. Right? If I want to diagonalize this, I first have to find the eigenvalues. Right? So I first have to find the eigenvalues. So the determinant of A minus lambda I, right, equals to the determinant of 1 minus lambda, 2, 4, 3 minus lambda, right, which equals to 1 minus lambda, 3 minus lambda, minus 8, 2 times 4. Right, so this equals to 3 minus 4 lambda plus lambda squared minus 8. So this equals to, this is right? Yeah. So this is lambda squared minus 4 lambda minus 5. Right? So this is lambda minus 1, sorry, lambda minus 5, and lambda plus 1. Right? So that means the characteristic polynomial equals to lambda minus 5, lambda plus 1. So that means the eigenvalues are going to be lambda 1 equals to 5, and lambda 2 equals to minus 1. Now what we need to do is to find the eigenspaces, because we need to find the eigenvectors. Eigenvectors. We need to find the eigenvectors. A couple ways to do it, to be honest. So for lambda 1, I want something like, for lambda 1, I want A times xy to equals to 5 times xy, right? So this would imply 1, 2, 4, 3 times xy to equals to 5x, 5y. So I have this.
Is this necessary? Isn't the diagonal matrix just the eigenvalues of A?
Yes, but I'm looking for Q. I'm looking for the
The inverse.
in the front and one in the back. which are comprised of the eigenvectors, right?
Okay.
Yeah, so I need to find what the eigenvectors are. So this is going to be what? X plus 2y equals to 5x, and 4x plus 3y equals to 5y. So what is this? This basically means minus 4x plus 2y equals to 0, and minus x plus 3y equals to 0. I am way too lazy for this, so I'm just going to use Symbolab. Yeah, I can use Symbolab. So I don't know how to use Symbolab though. How do I do this? Oh wait, no, there's the eigenvalue thing. Ooh, I can just use this to compute the eigenvector because I'm too lazy.
Isn't the bottom one supposed to be 4x minus 2y equals 0?
Yes, it should be. Sorry about that. Thank you. Okay. Okay, Symbolab, please tell me the truth about the eigenvectors. So it's going to be 1, 2. Yes, 1, 2, 1, 2. Yes, so for this one is 1, 2. So x, y is going to equals to 1, 2. So this is going to be an eigenvector for lambda 1. Now we just need to do eigenvector for lambda 2, 2. Lambda 2, 2. Lambda 2, 2. Technically, I can just do substitution or elimination, but again, I'm too lazy. So for lambda 2, which equals to minus 1, what we're going to do is we want a times xy equals to minus xy, right? So this becomes 1, 2, 4, 3, xy equals to minus x minus y, right? So this becomes x plus 2y equals to minus x, and 4x plus 3y equals to minus y, which becomes 2x plus 2y equals to 0, and 4x plus 4y equals to 0. Oh, so it's just 1 and minus 1. These two are just negative of each other. How nice. Right. So we have the eigenvalues, which is 5 and minus 1, and we have the eigenvectors, which is 1, 2, and 1, minus 1. Now we can assemble our result of diagonalization. Right. So A equals to Q times lambda times Q inverse, right? So Q is our eigenvectors, which is 1, 2, and 1, minus 1. And our diagonal matrix, which are the two eigenvalues, which is 5 and minus 1. And times what this 1, 1, 2, minus 1 inverse is, which I do not know. But I know one thing that will tell me what the value is. So I need to find where's inverse? Oh, it's right here. Inverse of, or I can just enter the matrix and just to the power of. Right, so this is 1, 1, 2, minus 1, and this entire thing to the power of minus 1. Something like that. Right, so the inverse is going to be 1/3, 1/3, 2/3 minus 1/3. Of course that is the case. What was I thinking? I forgot the formula for doing 2x2 inverses. Whatever, I don't care. Right, so this is the result of our diagonalization. Now, what we want to calculate is we want to calculate a to the power of 3 minus 5a squared plus 3a plus I. Right, so we want to diagonalize this. Okay, let's look at what each single one of them equals to. Let's look at what a3 equals to. A3, a cubed. Well, a cubed is just q lambda cubed and q inverse, right? Which is just q times this cubed, which is 125, 0, 0, minus 1, times q inverse. So this is a cubed. Let's do 5a squared. What does 5a squared equals to? Well, this equals to 5 times q lambda squared q inverse, right? Which equals to q times 5 times, because remember 5 is just a number, so it is always commutative. What is a squared? 25 and 1. Q inverse, which equals to q which equals to q 125, 5, 0, 0, q inverse. And what's 3a? Well, we know what 3a is. 3a equals to q 3 times the inside, which is 5 and minus 1. Q inverse, which equals to q 15, 0, 0, minus 3 times q inverse. And what is I? Well, I, can you guys see down here? You guys can see down here, right?
Yeah, we can see it.
Okay. So I is just going to be q times I times q inverse. Oh, okay. So what does this equals to? Well, this equals to q times 125, 0, 0, minus 1, q inverse plus or minus q 25, no, not 25, 125, 0, 0, 5, q inverse plus q 15, 0, 0, minus 3, q inverse plus q identity q inverse. And I mean, distributive property, we can just factor stuff out, right? This equals to q of basically the inside added together, right? So let me just write that stuff down so it's clear. So this equals to q of The first matrix, 125, 0, 0, minus 1, minus 125, 0, 0, 5, plus 15, 0, 0, minus 3, plus 1, 0, 0, 1, and the entire thing times Q inverse. Oh, I mean, it's already in a diagonalized state. So this is Q. I guess it will be 0. No, not 0. So 0, 15 plus 1. I don't know, 16? 0, 0. Minus 6, minus 9, minus 8. It is already diagonalized, right? So that's it. This would be, you cannot see this, but yes, you can. Right? So this is already diagonalized. That's it. Right? And yes, for 3, you just diagonalize this and raise this to the 100th power. Raise this to the 100th power, which you can do for this. I don't know what 5 to the 100th power is. Right? 5 squared is 25. 5 cubed is 125. 5 to the power 4. I don't know what 5 to the power 4 is. 625. And then it's like what? 3125. And then if you square that, equals to something. Wait, so 5 to the power 3, 5 to the power 4, 5 to the power 5. So 5 to the power 10 is roughly 10 to the power of 6. So this is in the order of magnitude. 5 to the power of 100 is roughly in the order of magnitude of 10 to the power of 60. So we're looking at something that is roughly 60 digits, which is a pretty big number. Do you know what 5 over 100 is? I mean, if you compute it, yeah, and then you just multiply Q and Q inverse. But just leave 5 to the power of 100 as 5 to the power of 100. Don't actually calculate it, because we are looking at a.
Can't you just take the diagonal of each, like the diagonalized matrix of each of the terms, and then just add them together?
Yeah, that's what I did.
Oh.
The diagonal of each one of the terms, and then I just added diagonal terms together, the diagonal matrix together, because I can factor out the Q in the front, I can factor out the Q inverse at the back, right? So I just added all of the diagonal matrices together, which is fairly easy to do, and then it is already diagonalized for me, so I don't have to diagonalize it again. Or, I mean, the other thing that you can do would be
brute force it.
Actually compute what this is and then diagonalize it again.
So any diagonal, the diagonalization of any diagonal matrix is just itself.
Can you repeat that?
If A is a diagonal matrix, then the diagonalization of A is just itself.
Yes. It will be I times A times I inverse.
Okay. Isn't I in
Identity. If A is a diagonal matrix.
Isn't I inverse just itself?
Yes, I inverse is also just itself, because it's the identity. It is the only matrix that is true. That is the inverse is itself. Okay. Yeah, and then similarly, how you do question 4 in the same way that you would do with question 3, right? Just raise this to the 100th power. You can realize that 6 is actually 2 to the power 4, and minus 8 is minus 2 to the power 3, right? And you can represent them in terms of 2 to the power of something. If you raise it to the 100th power, then 2 to the power 4 to the 100th power is just 2 to the power 400. This would just be 2 to the power 300, right? And that's it. All right, so it's 4 o'clock. I will have to leave this room. If you have any questions, of course, I have Friday office hours.
How screwed are we?
Not very. 6 is not entirely difficult.
I meant
or
for
at
our
least-
final, since Lord Savior overestimates our intelligence.
Yes. Whether or not it is an overestimation, I'm not quite sure, but he does expect you guys to know a lot. So
And also, what's gonna happen with the finals?
we do not know yet. So the result, I think, is a no.
No final?
No, not no final, but just we. I think the result is we rejected that. Let me check the quiz. Let me check the survey.
The new grading scheme is approved by majority of the students in this class.
It was approved. So survey statistics. Let's see. Oh yes, it is actually. It is approved 50%. So 50% of the students approved it. So then there will be a final. 62% midterm, 18% assignment, 20% final
Yes.
with Proctor U. It's just right now the problem is people are not very comfortable with Proctor U. That is something I do not know how Kylie is going to have to resolve it.
Oh my-
Because-
8 fucking people didn't respond. Holy shit.
I don't think Proctor U is his idea. I do not think that Kylie knows what Proctor U is. I think it was the chair that told him that Proctor U exists, and then the chair told him to use it for the final exam. Like, I am willing to bet that Kylie didn't even know that Proctor U existed.